So let's get started. Thank you all for coming. Today, we could call it the first seminar or the second of the summer series of 2023. And we're very happy to have a speaker who has flew all the way from Zurich to be with us today. Florian is a research engineer from Sony AI, and they have been doing an amazing work with not only research but deploying reinforcement learning to an actual product. And he's going to be telling us all the little things today. So, Florian, thank you, and the stage is yours.
Thank you so much, everyone. Yeah, I don't think I have to tell you too much about myself. I think Borja did a pretty good job already. Yeah, as you said, I work in Zurich at the moment. I'll tell you a bit more about Sony in general at the moment. But yeah, the general theme of today is our work on outracing champion Gran Turismo drivers with deep reinforcement learning. Next slide, please. Yeah, I will not keep you too long on our company, but since we're a rather new company, I'll just tell you some words about what we do so that you have an understanding of how this fits into our company vision. So yeah, we've been established in April 2020, so quite a turbulent time that we've been through so far, but also quite an exciting one. We have offices in Tokyo and Zurich where people work in person, and we have a big remote workforce in the US and in Canada. And a big part of our team who worked on this was actually based in the US and in Canada, working fully remotely on this. We have 4 flagship projects at the moment. The gaming one that I will talk about today, then a gastronomy one. People might be curious, what exactly does AI in gastronomy mean? Feel free to check out our website on this one. Imaging sensing, which is still rather confidential. And then last but definitely not least, and always getting more important over the years, is AI ethics. Just to give you some context of why Sony is so interested in deploying AI in this direction, I think it was the year 2021 or 2022, around 28% of Sony sales were made by Sony Interactive Entertainment, which you might know as PlayStation. So a big part of the revenue for Sony comes from gaming, and if we can use AI to make gaming more interesting and more engaging to get a certain advantage over competitors, then this has a huge value for the company too. Next slide, please. Some of you might not know about Gran Turismo. I have to admit, I didn't know Gran Turismo either when I joined Sony. It's been a while, it's been 4 years, so I know a bit more about it today. It's a simulation that we use in this project. So for some people, it might be just a video game. Some people might see it as similar to Mario Kart. But what is really important to understand here is that it's one of the most complete driving simulators. So it tries to very accurately model the complex driving dynamics, so the very nonlinear physics that come into play when you drive a race car at its limits. So the issue with that, or I would say the nice advantage of that, is if in a simulation like this, similar to real racing, you make the smallest mistake when driving the car at its physical limits, you immediately get off the optimal trajectory and have to start from the beginning again. So this is really, I would say, different from some bicycle models or so on that you usually use for simple car modeling. And because the physics here are so complex and non-linear that are modeled in this game, it's also quite complex to build an agent that is competitive with human drivers. So the agent that was shipped so far with this game was only able to beat around 20% of the community, and the other 80% just easily outperformed this built-in rule-based AI agent. So this makes this a very interesting challenge also for Sony to work on. Next one, please. So the focus of today's presentation is this work here that we published in Nature, I think around a bit more than 1 year ago on the left, where the challenge for us is we set up a racing event over those 3 different cars and 3 different tracks, where we race against 4 of the best drivers in the world in this Gran Turismo series. Now, there's not only Japanese drivers in Gran Turismo, but back then we were still in the middle of COVID. So due to geographical limitations, we race against those 4. I think they were all top 10, at least at one point in their racing career. And yeah, today I'll tell you a bit more about all of the engineering work, all of the research work that went into making something like this possible and making an AI agent that actually was able to beat those 4 drivers in all 3 tracks. Next slide, please. Yeah, so I'll tell you a bit about this AI of ours called Gran Turismo Sophy, or GT Sophy. It's named after Sony, so the So and Phi, which is Polyphony, the studio that develops Gran Turismo. And yeah, let's just start with the technical details, I guess. So one thing that you might also be familiar with from past reinforcement learning work, especially large-scale reinforcement learning work, is the importance of compute. So in this case, we started rather small with some of our earliest experiments. We had around 10 local PlayStations. At some point, I had 10 PlayStations running in my room, but it got a bit hot and hard to manage. So if you want to scale up like this and work on it with multiple researchers, you need a more scalable solution. So we had a great collaboration with Sony Interactive Entertainment. So you might know those guys just as PlayStation. So they have a cloud gaming service that I guess every one of you could sign up and use. And we were able to use some of those cloud PlayStations, actually in the end more than 1,000 PlayStations, to run the Gran Turismo simulation on it. And additionally, we had dedicated hardware for calculating the inference, as well as calculating the back propagation with that data that we collected on this hardware. Next slide, please. Yeah, this one, I guess this diagram is familiar to most of you, probably with some different colors and not round arrows, but you might know this from the Sutton and Parter book. But yeah, this is basically how our simulation worked. So we have the environment, which in our case is the Gran Turismo simulation, and the environment, as I guess pretty much everywhere in reinforcement learning, sends us the state that we'll talk about a bit more in the next step, a reward, and then our AI agent at the top sends an action that consists of throttle, steering, brake, and so on. Next slide, please. So what kinds of challenges does an AI agent need to solve to be good in a racing game like Gran Turismo? So obviously the first one that comes to mind to everyone is like, okay, you just need to be fast, so you need to control the race car at its limit. But then there's two additional interesting ones. So there's racing tactics, meaning when there's opponents around. At what point, for example, do you overtake? So often it's better to wait a little bit, even if there's already a possibility to overtake, because there's maybe an upcoming curve right after that where an opponent could re-overtake you again. And then last, but definitely not least, I think this is one of the points where most of our efforts went into, is fair play and racing etiquette. I'll tell you a bit more about negative examples in this direction in a second. But necessarily, it's similar to Formula One racing, where you often have those discussions of who was in the wrong when there was a collision in racing. There's debates for days and days and days. So you can imagine how hard it is to encode something like this into a reward function without the agent basically cheating and exploiting your reward function in some kind of way. Next slide, please. So for this very first task of driving fast, I'll quickly introduce some of our features and rewards that we have. So you'll see the big set here on the left. We have the three-dimensional velocity and acceleration of the car. Additional to that, we have the wheel load that the car has. Most importantly, I think this is a question that always comes up, is like, is this vision-based? It's not, and there are many reasons for that I'm happy to tell about more afterwards. But the way that the agent navigates here in the time trial setting is the agent just has vectors to a set of points that's on the center and sidelines of the track. So based on that, the agent knows about its surrounding track as well as the upcoming track segments, so that it can early enough decide when to brake, when to use the throttle, and so on. And then those features that I showed here are then mapped to a throttle and brake signal, so that's one continuous signal, as well as a steering angle. So in a one-to-one mapping sense, without any history. Okay, next please. So when we talk about the reward function, in a time trial setting, the goal is obviously just to finish the lap as quickly as possible. But something that's, I guess, a main problem in reinforcement learning is the attribution problem. So if you take an action in a certain state, how does this reflect in the reward? And if you just have the final lap time as a reward, this is obviously much too sparse to learn anything useful from it. So what we did is we developed a proxy reward that you can see on the bottom left in this dark green segment. So we reflect the agent's position onto the center line and see how much progress do we make on the center line using this reward signal. Now, obviously, you might say, okay, but if we just use the center line progress, why does the car not just drive along the center line? Like, how is it motivated to cut corners and so on? And I guess the answer there is pretty simple, that we just use a reward horizon. So if you accumulate this reward enough step into the future, then you have a pretty close proxy to the actual lap time, but one that is much easier to learn from because it's less sparse. Yeah, here on the top right, we did an ablation study looking at some of the features that we used. So we compared this course point to some previous features that we had that was based on LiDAR. LiDAR had some issues in that it was not dense enough. And if it was too dense, we sometimes overloaded the model in terms of having too much data, which made our whole pipeline slower. And then we also did an ablation of our reward functions, where we had our baseline, which was just which was the course progress, as well as a off-course penalty that basically penalized the agent for cutting corners and so on, where it was not allowed for human drivers. So we showed that if we leave away this off-course penalty, the action is actually even slower. Finally, we also tried a fixed step reward, where just every step that an agent is not done with its segment, it gets a penalty. But yeah, this did not even finish the lab because of this reward horizon issue. Next one, please. So I guess for those of you working in reinforcement learning, this is one of the more interesting or more important slides. So those were the main algorithmic changes that we made over what was already public in literature to that time. So we used the soft actor critic algorithm that I guess most of you working in RL already know. But we extended it with a distributional version and made it a quantile regression soft actor critic algorithm. So what we do here is usually in a Q-value function of a soft actor critic algorithm, you just have one output that estimates the expected value over a certain state. But what we have here instead is we output, I think it was a quantized distribution of around 32 buckets. So those 32 buckets model an expected range of values that are expected for this state as the agent is currently in. And we saw that this, you see it at the top left, performed much better in the time trial setting, as you will later also see in the versus setting. And we're also obviously looking into how this applies to other domains, but this is still work in progress. And our intuition here is why this works so well is in racing, as I quickly mentioned in the beginning, when you race the best possible trajectory, you're often very close to failure. So if you just go 1 degree too far with your steering angle, often you end up on the side of the track, and your return that you receive going that bit too far is so much different from the return you receive when you stay on that optimal trajectory, that we believe that in those cutting-edge cases, differentiation in the way that we model the Q-value function is very valuable. In addition to that, I guess a more common step that is often seen in RL papers is that we used n-step returns. So in this case, we used 5 additional returns. You saw in our ablation study, if you go up to 7 or 9 step returns, it gets even better. But then also the storage, there are some certain storage issues that appear when you go too long with those traces in your replay buffer. Next one, please. So one interesting thing here is, I guess RL researchers always like to show how cool their product looks in the end. But what I also like to include here is how bad it looks in the beginning. So just play, please. So at the top left, you see how the agent looks after 15 minutes of learning. So for context, this is 15 minutes of learning, I think, on 10 playstations with 20 agents each. So those are parallelized by a factor of 200. But still, already after 15 minutes of learning in real time, this agent is able to complete the track. It's very wobbly. It's not really using a good racing strategy. But then, yeah, you see, after 4 hours, you already have something that is comes closer to a fast policy. And then after 8 hours, the agent starts developing this out-in-out behavior that you know from, or you might know from real racing too. And then after 24 hours, I think you have an agent that already beats around, what was it, 95% of human drivers in time trial. So yeah, in the end, I think our agents are usually trained between 7 days and 2 weeks. The reason for this is that those agents are trained in real time. So what you might know from Mujoko Gym and so on is that you can just step through your environment as quickly as possible. But this is running on a real PlayStation game, and changing this game in a way that such kind of stepping would be possible and efficient was just not feasible for this work. So we had to work around those constraints for this project. Next slide, please. So yeah, here are the results of what this looks like. As I said, again, in around 4 hours, we learned some driving, and around 8 hours of training, we're around the same speed as the built-in rule-based AI that the game developers included for this game. Around 24 hours, I think we beat around 90% or so of the human player base. And then you see the final performance at the bottom compared to the top 5 humans in the world. And the orange is the distribution of 100 lap times. So it's not perfectly accurate over each lap, but you see that in almost every lap we beat all but the best drivers. And something to point out here is also those human lap times are just the best of their lap times for around 100 or 200 laps. So meaning on average, we easily beat against the human drivers in time trial. And then here on the right, you'll see what this then finally looks like in the time trial mode. Play, please. So this is one of the chicanes that is often feared by human drivers. You'll see why in a second. So this is where most of the crashes appear in human races. And obviously because of the precision of an RL policy that you can deploy at that frequency, obviously this is no issue for our agent. Next slide, please. So yeah, obviously you saw our agent is super fast, but the question for us was, where is the agent faster than a human player? And when you look at the bottom left there, this is on this SAR track, you can see the colored segments where we make up a lot of time on the human driver. And when you see those visualized on the track, it's always in the tight turns. So what you see here on the right is human top driver. I think he was Gran Turismo champion last year or so, commenting on the ghost trajectory on our driver on how it behaves. Next, please.
It gets way more difficult to do the same things, and they can react like very, very quickly. Man, that's fast. That's really fast. Like I really want to watch the onboard as well to see how like they throttle and braking phrase, steering phrase as well. Work, because it's definitely something else.
So what the driver was referring to here is the onboard telemetrics. So what Igor Fraga was really interested in is seeing what kind of actions does our agent actually take. So could you go to the next slide? And this is really connected to one of the questions that we get the most, I think, next to does this learn from vision or not, or why does it not learn from vision? The question is this fair, the way we evaluate it against a human? And one of the important factors here is reaction time. So our network communication actually gets us to a reaction time or action inference time in total of around 23 to 30 milliseconds, which is rather fast compared to humans. So if you have a healthy human, adult human, you're around the reaction time, I think, of 200 milliseconds. Please correct me if I'm wrong. That's the latest number I remember. So we're still quite a bit faster in terms of inference. But one test we did for our work is we introduced artificial delays to our inference. So we deployed our inference with a delay of 100, 200, and 250 milliseconds. So even with those delayed inference, our agent learned to actually drive faster than the fastest human driver. So from this point, it's not as much of an issue. Another issue or another question that often comes up, our agent can just directly output any kind of steering angle or any kind of throttle value without any blocking on how much movement they can do. So you can see on the bottom left there the steering angle of our agent in orange that looks not as smooth as the human angle in blue. But what we now figured out in the meantime is if we apply some kind of filter on this that makes the angle look the same, we are still very much faster than the human in this case. So this is also not as much of an issue. One thing that was really interesting is there was often this theory by human drivers that our agent is just faster by being able to brake later. So by being more precise, it could just brake later, and because of that, it's faster. But then it turned out that in certain curves, our agent actually brakes earlier, which was a nice indication that our agent not only is able to have the same strategies as the human drivers, but more precise, but often also smarter strategies or better ways to approach a curve. So yeah, play please.
From the AI driving that I could take to myself, and maybe with some twist, I think I can adapt something to myself as well. So it was like very, very interesting.
Next one, please. So yeah, so far a very important component has been missing here. So far it's just the agent driving on the track by itself. And obviously it gets much more complex when we add additional opponents, because in this direction, obviously there's the whole complexity of predicting what the opponent's going to do. And obviously not every opponent is the same. And when we learn an agent against other agents in a game, those other agents might behave very differently from human drivers that we wanted to evaluate against in the end. So next slide, please. So the very first step to having opponents in a race is obviously seeing them. So what we did in this case is we extended our observation space with this grid, which had a kind of list for cars in the front of the agent and cars behind the agent, with I think probably, what was it, 80 meters in the front. So that's approximately matching with the view a human currently has normally has over the track, and I think 20 to 30 meters in the rear. And for each agent that was inside this grid, we had the relative position of this agent compared to of this opponent compared to our agent, the relative velocity and the relative acceleration. We then also figured out for our agent to be motivated to actually overtake the opponent, we needed a new reward part that motivates the agent or rewards the agent based on the delta in progress it can make compared to opponents around it. The main issue is if we only rewarded the main progress on the track, our agent figured out that it was safe and easy to just stay in the slipstream of the human driver or opponent driver and basically exploit the reward in this direction. And next slide, please. So yeah, I already mentioned this sportsmanship in the beginning, but this was one of, I think, the key points in our work. So this was really hard to balance. Here on the left, you can see a video of what happens if you don't balance the sportsmanship well and tune the reward in a direction that makes the agent a bit too aggressive. Play, please. So this was on one of our This was one of our initial agents that didn't have any collision penalties at all. So this simply had the goal to make as much progress as possible and overtake as many opponents as in any way possible. We then started experimenting with different collision penalties. We, for example, had one collision penalty that was based on the delta in velocity between the human driver and our agent. And something our agent then learned is it can just very slowly push off the human driver or the opponent driver off the track. So as I said initially, it's not only hard for humans to set up a rule book for Formula One, But if you then give this rule book to a reinforcement learning agent, it will for sure learn to exploit this reward function. So we started adding additional reward parts, like specific reward parts for collisions that we saw pop up frequently, like a rear end collision, any kind of side swipes and so on. And maybe one thing that I should also mention here, since we had this overtaking reward before, that motivates our agent to get as much distance on the opponent as possible. Obviously, the easiest way to achieve that is when the opponent is off the track. So we somehow wanted to counteract with all of those rewards. Now, one issue that we run in is, obviously, if you put too much weight on those rewards, or if you use the wrong rewards, then your agent just stays away from any kind of chance of a collision or any kind of probability. And obviously, if you drive against an unpredictable driver like a human driver, and you want no collision at all, then obviously you cannot race competitively. So here on the top right, we'll show you a quick video of what this looks like in a competition. So this is our agent in orange and the human driver in white. So might have been a bit much at once. And yes, we had actual commentators on our races. But what happened here is the commentator pointed out, like, oh, okay, our agent is in front. I think that was at the last lap of the race, pretty close to the end. And the commentator said, okay, now that we're through this segment, there's no chance that the human's going to overtake the AI anymore because there's no segments coming up anymore for this. And 2 seconds later, the human overtakes our AI. And obviously, we're thinking, like, what's going on here? What's wrong? And when we analyzed the replays, and that's, by the way, something we did spend a lot of our time on, we noticed that the second our agent is right next to the human driver, our agent goes off the throttle. And the reason for that is if our agent would stay on the throttle, our agent knew, okay, the chance of a collision is quite high. So this was the other end of this spectrum of having then in the end an agent that is way too timid. And I think the main goal of our work overall here was also to find the sweet spot in between. And obviously, if you talk about reinforcement learning, reward function tuning is not exactly very sexy. But if you want to make something into a product and use something in the end commercially, then I think reward function tuning is a big part of reality, unfortunately. Next slide, please. Yeah, regarding our approach, there was one additional thing that was very important, and I think probably also not as clean, as sexy as you might know from pure self-play in literature. But something that we did here, or sorry, I shouldn't say self-play, but pure random initialization play. But something we did here is to get our agents started in very interesting racing constellations, we defined a set of custom launching scenarios. So something that you might see here is at the very top in purple, there's the scenario of the start. Now the start is very important for our agent because start is where usually most of the collision happens because all of the cars are sitting right next to each other. So we made custom scenarios where we said, okay, we practice the start more. We also have some scenarios where we initialize our agent right behind an opponent such that there's more opportunities to train for behaviors like slipstream and so on. Now again, if you have an infinite amount of data and an infinite amount of simulation restarts, then obviously you can start randomly and you'll get enough of those, I would say, interesting situations. But if you're restricted with the number of rollouts and number of simulations that you have, then the initialization of your environment plays a very important role of the value of the data that you finally end up with. And I would say in a very similar direction, an additional thing that we did is when we constructed our mini batch sizes that you can see on the right, or our mini batches, each of those scenarios were put in a separate replay buffer. So we had a replay buffer that only contained slipstream samples. We had a replay buffer that only contained grid start samples. And then with a fixed proportion, we sampled from each of those replay buffers to make sure that each of the skills that are relevant for our agent to learn and to maintain over the whole course of training, that each of those samples are represented and not forgotten over training time. Again, if you can infinitely scale up your simulation and infinitely scale up your rollout, it might be okay to just randomly sample. I think we just talked about it before. In certain papers, you can have batch sizes of 100,000 samples. This wasn't really possible here. So I think with tricks and approaches like this, they were very, very relevant to keep our agent to maintain those skills over a long training time. Next slide, please. So obviously, as you do in papers, we once again conducted an ablation study to show which of those measures actually had an effect. So you can see at the very bottom that when you don't introduce that passing reward, obviously your agent is not going to perform well, as is measured here in our team competition score, because our agent's just not motivated enough to overtake. Then our next data point there is, okay, we have the passing reward, but we just have a singular replay buffer. And then you can see, okay, if you add this separate replay buffer in those different scenarios that we are evaluating, our agent is much better at maintaining those skills over a long time. And then in the end, we also introduced some PID opponents. So those are basically very simple opponents that just follow a straight, like on this scenario here on the right. And everything our agent had to learn is to just stay in the slipstream and then make an overtake in the end. So play the video, please. So yeah, this is one of those scenarios that I introduced before. This is the slipstream scenario. So what our agent learned here is it's important to stay in the slipstream long enough to gain enough momentum to overtake. And then what our agent additionally learned is try to fake a pass on the left. And then what agents often try to do, and also human tries to do, is to block on the left. And there our agent kind of tricked this other opponent and overtook on the right finally. Next one, please. So one thing that was very important for the final behavior of our agent was what kind of opponents it trained against. We first started training just against the built-in AI. Built-in AI is a rule-based approach. It's often very kind. It often makes space when there's an opponent coming up. And what we found out there is, okay, if you just train against this built-in AI and then evaluate against human drivers, our agent is just too used to other cars giving space when it's coming up. So that doesn't work. Our agent ended up much too aggressive. On the other hand, if we evaluated our agent against other very aggressive versions of itself, our agent turned out way too timid to make smart or rather aggressive passes against human drivers. So we finally ended up with a mix of using the built-in AI as opponents, but also using other versions of Sophy, so other self-play model clocks of this opponents as of this agent as opponents. And then finally, there's this PID controller that I showed you previously for slipstream training. Next slide, please. So again, I think this is one of those parts of RL that isn't often talked about because it's not particularly sexy. Optimally, if you train an RL policy, you just train it longer and longer, and the longer you train it, the better it gets, and you just take the final model and you deploy that, and all is fine. But what we found here at the top right is you have two skills listed here. One skill listed here, which is the slipstream test. So the slipstream test is you start in the scenario that you saw in the video before, and you see if towards the end of the straight our agent made an overtake movement or not. And hopefully it didn't include a collision. And what we see, even at an agent that trade fairly long, we still see certain skills come and go. So even if this is included directly in the training, we see this come and go. So we obviously have different skills that we want the agent to have. Slipstream is one of them. The starting scenario without any collisions is one of them. So what we ended up doing is, let's say on the left, we have those different colors symbolizing the different runs that we trained. And each of those little triangles is a different a model at a different epoch for each of those runs. So we applied some initial filtering to that. For example, checked, okay, what was the lap time that an agent like this achieved? If it's like over a second off from our best lap time, we probably don't want to consider that. How many collisions did it have in it? Evaluations that we ran parallel to training and so on. So we created an additional first filtering. After this filtering, we created a so-called N-of-1. So this is a series of scenarios that we designed. One of the scenarios is the slipstream evaluation that we showed you before. Another one was a grid start, where we see, okay, how many collisions are there and so on. Based on this N-of-1, we did an additional scoring and then have a selection of those policies. And with those policies, we then finally launch a PvP, or player versus player evaluation, where each of the candidate policies is run against each other, and we then have a final set of metrics. And then let's say, usually I think we have between 2 and 4 candidates that we thought were valuable. But then again, those so far were only evaluated against other AIs. So this could be the built-in AI or some of our own AIs. But then the most important thing for us is like, how do those perform against humans? So before we raced those against those top drivers, we also had some internal test drivers at our companies that we evaluated them against and got very important feedback from, so that we could then finally make a decision based on this. Next slide, please. So yeah, talking about all of those details now, obviously I'm very happy to share what the final outcome is and show some more cool videos of what actually happened in this race. Next slide, please. So here you will see the start of the race at the track called Seaside. You'll see, again, the human drivers in the white cars and our AI agent in the color cars. And as I mentioned briefly before, the start here is one of the most crucial parts, because if you can pull away at the start, obviously, you have a big advantage for the rest of the race, I guess similar to Formula 1. And also, it's the part where collisions are most likely to happen. So you'll see one of our agents here, the purple Sophy, is able to use the slipstream of another agent, of another opponent early on, and is able to make an outside pass and pull away quite early. So play, please.
Into the slipstream to try and get a run on their fellow competitor. Only Bordeaux does not have the advantage then on that slipstream. Into the braking zone, turn 2 we go. It's a lunge from Cockerman as he tries to go up the inside, but it's actually Sophie Violette who goes on the outside into turn 2. Very aggressive driving then from Violette and up into second position at the end of the first corner. So it's now the 2 GT AIs that are in the...
So yeah, you had the agent start, I think, in 1st, 3rd, 5th, and 7th place. And just after this very first corner, the agents are already in 1st and 2nd place. And because of this time trial performance that I mentioned before, obviously the humans, unfortunately, have no chance of catching up anymore. Next slide, please. So this was a really exciting one that I think ties a bit into the direction of making long-term decisions. So something that you see here is our agent comes into a position where it's kind of implied by some human drivers that the agent should make an outside pass, but then you'll see our agent decides against making it because possibly the probability of a collision was too high in this case, the possibility of not making the pass and then losing some space. And so instead you'll see the agent patiently waits and then finally gets into some slipstream and makes a pass in a next segment. So play, please.
Down towards turn 17, could an opportunity present itself then here for Bear? Well, going defensive then is Yamanaka. Bear goes towards the outside. This is getting pretty close between them as they run side by side into turn 17. Yamanaka holds firm to the inside line, and Bear is not able to get themselves past them and through and up into 4th position for the time being. So, over the timeline we go. This is where the slipstream, though, of course, will help Sophie Bear as they come down towards turn 1 and then into the braking zone of turn 2. You can see the lift off the throttle there for Bear, just don't get too close behind coming through those series of corners. Big old bit of opposite lock as we come down the inside. Miyazoto's trying to go through there as well, but not close enough. There goes through on Tomoaki Yamanaka though for P4, so aggressive and robust driving from the AI then as they move them himself up a position.
Next slide, please. So one thing that I've often heard from people not too familiar with this matter of racing is like, why is this so hard? It's just an agent following a line. You can just predefine this line and everything is fine. I mean, in the time trial setting, it's already not that simple, but let's leave the time trial setting away for a second. But as soon as you have opponents around, it gets much more complex because your opponents might behave very differently, and you need to adjust to the situation that the opponent brings you in. So what you will see here in those coming 3 videos is that our agent learned to behave very situational. So based on how the opponents around it behave and where there are opponents, the driving line of our agent changes significantly. So in the first video on the top left, you'll see our agent just driving solo, so doing this classical out-in-out trajectory to cut the curve optimally. Next, please. So you'll see this is fairly standard. It starts from the left, goes in towards the right, and then out towards the left again to maximize the radius and therefore also maximize the speed that it can go through that curve with. So yeah, what people say is like, oh, okay, why don't you just learn that and then just do this over and over again? Now, next video, please. What you see here is the video that we just had before. Our agent tries to make a pass, but then the human obviously is in there and our agent cannot just push through. So our agent needs to be able to keep enough space to later on make the slipstream pass. And then for the next one, please. This one I think was the coolest one for us to see, because what our agent learned here is, it first looks like our agent would would try or attempt a left pass. The human driver tries to block on the left side, but the agent very quickly and very smartly then tricks the human driver and finally makes a right pass. Here's another example of how this behavior of our agent is very contextual. So what you see here on the right plot is the pink curve. This is our agent driving during this race against other humans, but when no other drivers are around. So you see this very typical out-in-out trajectory. And what you'll see in a second is you have our agents here marked in green and gray. So there are 2 of our agent drivers against the human drivers, which are marked in blue and in yellow. And our drivers start our AI drivers start in a slightly disadvantageous position, but through very smart team behavior and through optimally using the slipstream here, are able to make a double pass out of this situation. So play, please. So you'll see our agent falling back initially, but then via sticking through that slipstream, are able to make this double pass here, which I think was quite surprising also for the human drivers. And next one. So finally, obviously, when we work on something like this in RL, our biggest interest is what does the community think, right? Do they think it's cool driving against that? So we, after the event, we made some interviews with the human drivers who participated against our AI, both in the versus setting here as Tomoaki Yamanaka, as well as the time trial setting with Emily Jones, who was nice enough to join remotely for this experience. So one really cool thing that Tomoaki Yamanaka said here is that by seeing our AI drive and by being able to drive against the AI himself, he was able to see that he is currently not at his limits. So in many racing situations where he previously thought there is no way to make this better or there's no way to improve over himself, seeing the way our agent drives, he now knows that there's still some potential for himself to improve himself. So this was really cool. And then there's a testimony by Emily Jones.
It's really interesting seeing the lines where the AI would go. So there were certain corners that I was going out wide and then cutting back in, and the AI was going like in the whole way around. So I learned a lot about the lines and also knowing what to prioritize. Like the AI into turn 1, for example, I was braking later than the AI, but the AI would get a much better exit than me and beat me
So I think that's one of the parts that makes this really fun for human drivers also to drive against, is that they can find new ways to play the game and new ways to be better at this game. Next slide, please. So tying into this, one thing that was super cool for us is that we got the opportunity to actually get our AI into the game. I think this is one thing that sets this project apart from many other RL projects. Like if you think about certain other RL teams that worked on games before, often you have this huge paper of like, yeah, we're superhuman, we bet the world champion and so on. And then this just vanishes. And the community, I mean, obviously the community can watch the replays, but the community never has the chance to drive against or to play against those AIs. And in this case, it was really nice that together with the Polyphony Digital team who produces the game, we had the possibility to actually get the agent into the game. And this, I think, was in February and March of this year for an initial test period of 2 months. Next slide, please. So what we did here is we trained Sophy, our agent, for 4 different tracks. And on each of the tracks, you can see here on the right, the human driver drives against 4 different versions of Sophy. So our agent learned to control different kinds of cars. So some cars, obviously, because they have lower horsepowers, are just naturally slower. So our agent still tries to give its best. It still uses the same reward function for each of the cars. But then the difficulty is naturally modulated based on the human having an easier car or a faster car to drive with. And then in addition to that, we have this expert mode where the human driver can try driving against Sophy in the very same car. And now I tried it myself. I failed miserably. But there are some drivers that were able to pull ahead on the very first few meters and then just able to block in all curves and win this way. So I think this mode was specifically entertaining for the very best drivers to learn how to block well on those different kinds of tracks that we provided. Next slide. So yeah, I mean, images don't tell that much yet. Here's a short video of a Gran Turismo YouTuber playing this new Sophy mode. And you can see the human driver's car in white, and then the different Sophy cars in the colored cars. Play, please.
Sophy blue or blue, which will start in pole position or basically in front of the whole pack. And essentially, it does put up a good fight. It's definitely a step down from Sophy Violet, which I will talk about in a minute. But it will fight you and it will battle you. I definitely noticed that the blue one was a lot more dynamic than the likes of the red or the green. So do expect to have a few battles with that one. It will really defend from you. It will try and predict everything you do. And then we have the start of the show, which is Sophy Violet, which is the car that will start behind you in the multi-class races and essentially attempt to chase you and the rest of the pack down. And it will. Whilst definitely it's easier when there's more cars on track because of, they will battle each other, Sophy Violet will definitely put up a good fight. It really will just dive at any opportunity it gets. It definitely isn't stupid and it will back out of moves, but it will basically take advantage of any gap you leave.
So what's also really interesting here, it was basically the same RL approach, just deployed on different car models. And what we see a lot from the human user base is that they start interpreting different character traits and personalities into the car. And it's like, yeah, this car is definitely more like this, and this car is definitely more like that. On the RL side, it's all the same. But it's really cool how the community often humanizes what our agents are doing. And it's like, okay, I hit it before, now it took revenge on me. We didn't implement revenge at all. But often the humans start interpreting traits like this into our AI agent. Next slide, please.
Why did Sophy Violet have a sad face about that?
Oh.
Can the AI PM the other player?
Yeah, so there are some emojis implemented based on, this is not AI based, this is rule based. There are some emojis implemented based on how the humans behave. So if there's a crash, if the human overtakes, and so on. But yeah, I don't know about the details of that implementation. Now, obviously, as before in our racing event, also here for the product, we were interested in like what has the community to say, because many of our team, we don't know that much about Gran Turismo. Obviously, we played it ourselves many times now, but we're not in this hardcore scene as many people are. So we checked out Reddit, we checked out GT Planet, which is the biggest online Gran Turismo forum, and we wanted to see what do they have to say about the kind of product that we made here. And I think the best thing that we've heard was from Jordan Greer, who's the GT Planet founder, who said, GT Sophy is like having your best human rival online all the time, ready to race whenever you are. So I think this is a pretty nice description of what the advantage is of having this kind of technology. Because usually for human drivers, when they, especially for the very top, when they want to compete against someone at the very same level, they need to be online at exactly the same time. They need to be lucky enough to be matched with someone at that level. So if you have an AI agent that is very similar in behavior, who can replace that, this is a huge value. And Jordan Greer also said that this is a very great way to practice your racecraft. So when I talked to him myself in person, he said, this might also be something that's very cool for human, like actual races, for actual race cars, if you can practice against an opponent like this, even only in simulation, with such a consistency and such a aggressiveness in certain parts. And there's also from everyday players some great feedback. This Reddit user saying she's fantastic. The way she drifts around the last corner at Tsukuba is the exact opposite of how the normal AI behaves. So what's very important to understand about the normal AI is it's rule-based. So whatever the AI does, if you played the game for 10, 20 times, you exactly know what will happen. With an RL agent that's based on a neural network, you're often surprised by what's happening. And in this case, the AI agent drifts around the curve. And because the drifting dynamics are especially difficult to handle, this is something that a rule-based agent usually would never do. So this kind of unexpected behavior is something that users were very happy about. Next one. OK, I'll hurry a bit. Just some of the changes that we did from our Nature paper to this. Obviously, we implemented this for different cars. As a way to modulating the difficulty. And then also we tried to make the AI a nicer driver so that humans could drive in a similar way. So we modulated the reward a bit such that the behavior becomes more human-like. OK, last slides. So upcoming challenges. Now, as I very briefly pointed out before, our policy is currently a one state to one action mapping, meaning there is no history in the input, or there's no kind of history in the output either. So something that might be interesting in the future is looking into more strategic and elements of this. So for example, currently tire wear is not enabled in this race. So if you drive hard on the tires, this is not an issue at all. But in real racing, if you use off the tires, you will suffer from this in the long term. So this is a very long horizon issue to solve. So that might be interesting. Generally, explainability might be interesting to know. And then also applying this in this kind of algorithmic knowledge that we gain from here in other domains. Last but not least, one of my favorite videos here is, so far we had one kind of driving style that our AI developed. It just tried to drive as fast as possible. But in reality, driving fast is not the only goal. So what could also be interesting, and here is a short teaser for this, is driving in different styles. So it might not be the most efficient, but I think directions like this could definitely also be interesting. Next slide, please. Yeah, just very quickly here. Those are all the people who worked on this initial Nature paper. So this was a great team effort. So it was just very important for me to to include this also into our slides to show all the faces of the people who participated here. And then I think, yeah, we can go to the questions. Thank
you. Just to mention before, yeah, people leave, we will have some food as always, courtesy from our sponsor DeepMind. The next talk will be on the 7th of June with Andrew Lampinen from that company. And yeah, like people who are online who, if you want to stay, you can ask questions on the chat and we will read it a lot. So we have some here, so we're gonna start.
Thank you very much for the presentation. I wanted to ask about the study of the behavior of the system in out of distribution situations. In the sense that, for example, you talk about using different cars, and you mentioned that there were three different circuits. So what was if there was some specific study regarding this question of what the system is going to do when you are sampling a case of situations that is not similar to the one in the training?
Yeah, I mean, in versus behaviors, we see a certain kind of generalization. Again, we don't include every kind of pass right in our training data. So we see a generalization in terms of what kinds of overtakes we can do in other unseen situations. But again, there, as you saw, we needed to include very specific scenarios like slipstream passing and so on. So there it was often important that a very specific scenario was contained in the training. So generalization there was only to a certain degree. Then in terms of switching cars off or tracks, I think very early on in the previous work, we did a test where we just deployed a car train on one track to another track. It learned to drive around 4 or 5 curves, but then just crashed and couldn't recover anymore. Similar for a different car. One test we did make is we gave a car better tires with more grip. And I think in this scenario, if I remember correctly, our agent was able to complete the track, even though it didn't learn about this. But obviously, there are many approaches where you can just train with this goal in mind, right? I mean, so far, this was not really a goal, but let's say you have a goal of supporting all possible unseen tracks or anything in this direction, then you could adjust your training algorithm or your curriculum to include more varying tracks, as well as any kind of randomization or input augmentation to adjust for this purpose. Yeah, go ahead, please.
So one question that's slightly related to the one you just asked, a completely unrelated one. You've mentioned trying on different tracks. Have you seen any advantages, or have you even tried to use pre-trained cars that really work well on one track to see if they would learn faster on another track? And my second question that's unrelated is, you've mentioned combining reward signals. Is it just weighted combination of scalar values, or is there something more fancy than that?
Thanks a lot. Regarding the first one, yes, we tried this, if I remember correctly. And we also tried behavioral cloning as quick starting. But the issue is that with our pure model-free RL approach, or issue, or I could say advantage, is that already after an hour or two of model-free RL training, we're already at a point that is pretty good. It's not quite there yet, but it's pretty good. And this is a point that we did not achieve when we did fine-tuning of another model that was trained for a different car or a different track. And also that's something that so far we didn't achieve with behavioral cloning. So at least till now, the solution for us is still just to start from scratch, because those 2 or 3 hours of head start just don't make that much of an advantage in a 2-week experiment. But it is definitely interesting for us because sample complexity is very valuable. I mean, if you want something like this in a product and you have a new version of the product and you need to change something, then starting this again and running it for another 2 weeks is obviously an issue. So everything that increases the sample complexity is very well appreciated. And the second part is, yes, it is a linear combination. So obviously some reward parts are quadratic, like quadratic pace and speed, but in the end, it's a linear combination based on different reward terms. Yeah.
For this like curriculum of initializations, how much tuning did it require? And also like tuning the relative frequency of the occurrence of those initializations in the batches. Was it like really finicky or?
I didn't directly work on that part, so I cannot give a too detailed answer, but I think we spent at least some time on it. And I mean, what I can say, it was necessary, right? I think the main takeaway here is it didn't work without that. And I think the main reason for that is that often in other RL applications, you just have so much data and so many different random initialization that it's not necessary. But as soon as you're in such a low data regime, it becomes necessary. Yes, please.
Not so much on the algorithm itself, but going back to your slide with all those people on it, something I've always been curious about on these papers that have so many people, and you just mentioned that you didn't work on one part of it. How is the team broken up? Like what tasks were people given? How are teams allocated?
That's a really good question. Thank you. So generally, there was this big divide of our platform team. And I think this platform team was super crucial for this work. So what they made is they built this infrastructure for us to be able to actually effectively use those PlayStations. So you might expect, okay, sometimes a PlayStation dies for whatever reason. There's an error, you don't know why. Back in the day when I had those PlayStations in my apartment, I had to run to the PlayStation, turn it off, turn it on again, and restart the rollout worker manually. So to have a platform where you can just very reliably start an experiment and everything will be handled in the backend, your experiment will just run for 1 month without any issue. This was a big part of it. So I think this was maybe 30–40% of our team. Then we had one part of our team that was mostly focused on AI engineering. So developing algorithms, making sure that our libraries are stable, making sure that our libraries are working. And then one part that was more in the research direction. And there, I think the team constellation changed over time. So in the very beginning of the project, we tried to go as wide as possible. So we had some people who tried like, oh, okay, how could we do something model-based? How could we do something vision-based? What is the best way to improve our model-free approach and so on? And then I think the longer we went, the more this distilled into, okay, we're actually getting closer to our deadlines. We want something feasible. Let's now put all of our power on this most promising thread. Okay.
Yeah, thank you very much for your talk. You mentioned style in the Outlook. Would it be possible to achieve some kind of modularity? So dial up and down the performance and only beat 60, 70, 80% of players and a little bit more aggressive and a little bit cooler? Would you use different reward functions or would you just jump to different points in training time to match the description of whatever you want?
This is indeed very interesting. Since it might be related to ongoing work, I cannot really comment on that. But it's definitely, I think, interesting if you could implement something like that to our product. Because that's something also the community asked for. It's like, sure, your AI is very good. You can dial it down by giving the AI a worse car, but this feels bad, right? If you're in a Ferrari as a human driver and you have your Fiat Cinquecento almost speeding you, this doesn't feel right. So yeah, something like this would definitely be interesting for us.
But you cannot explain how you would kind of approach a problem like this.
No, I'm sorry about that. I mean, you can join us and then we can talk more about it. Go ahead.
Just two really high level questions. The first one, in your opponent modeling, you gave the AI the relative position, velocity, and acceleration. How robust is it to noisy measurements? Is that something that you guys looked into?
That's something that we indeed looked into. I cannot give you any accurate numbers, but something that's interesting in this direction is that if you give the agent noisier observations, obviously the agent cannot be as precise and as aggressive in this direction as I guess will be expected. So I don't think we have any exact numbers in this direction. One thing we do have numbers on is if we in time trial mode add noise to the information. And I think up to 5% uniform noise is still fine for the agent to complete the lap in a superhuman time. But for the versus setting, I don't have any exact numbers.
Second question. In the model selection that you guys did, there was a point where you went from the model versus model to PvP type experiment. The training against a human. How much of a drop in performance was there in moving from one to the other?
So we didn't do the exact same test with the humans because basically the tests that we did in PvP or in model versus model were quite extensive in the way that they did it. And we would in no way be able to get this much human playtime out of our test drivers. So we don't have a direct comparison, but there were often issues that only showed up once we evaluated against human drivers. So there were certain kinds of collisions that we didn't see before. Maybe you have a human that breaks much earlier than our AI agent is ever experiencing during training from other opponents. So there were many issues in this direction that started popping up. So we also tried to somehow adjust our training opponents in this direction so that this kind of human behavior is better reflected. Yes.
Hi, thanks for the talk. So I have two questions. My first one is if you had to compare the time for efficiently converting the real problem to RL, for example, designing rewards and states, and you had to compare this with the time for finding and fine-tuning generally training program model, which took more.
Sorry, could you the second point? I didn't.
The second part is basically the part where you need to choose between models and train them. And the first one is like to convert the real problem to RL in terms of designing rewards.
That's a tough one. I'm not quite sure on this one. I think the general RL idea was set up quite quickly, right? I mean, this idea of calculating the reward based on the progress along the center line, or the idea of having or overtaking reward, those came pretty early. So I think those ideas are already 4 years or so old. So this general RL framework, I think, was set up quite quickly. But then I would say, yeah, getting this last percentage in terms of performance, and especially in terms of sportsmanship behavior, this took months and months and months once we already had the initial setup going.
My second one is, how many car crashes do you think you had for reaching this like peak performance in terms of like hundreds, thousands, or millions, like in terms of magnitude?
Possibly millions, hundreds of thousands for sure. Yeah. I think one of my colleagues once computed the number of kilometers that our agents drove in all of this time, and it was something ridiculous. So yeah, I think especially if you have multiple agents in parallel. So here we have, I think in the versus experiments, we have up to 400 agents in parallel. In terms of playtime, you often get very quickly to something that a human could never play in their lifetime. So from this point, still very ineffective or inefficient. Yes, please.
So you're talking about some of the different styles the cars had that personifying, personifying. Were those styles coming from the agents being trained on the different cars, or what was creating those different styles?
Yeah, I think that was one part. So as the YouTuber mentioned before, it was like, okay, this car has this and this style and this personality. But in the end, it was the same RL approach trained on just multiple car models. So in this case, it was the cars. But often what you saw with test drivers, when they drove against one model, they're like, okay, this car now hit me because this thing happened 10 seconds ago. So they somehow imagined that our agent would work a certain way just because humans work that way, right? So when you hit a human opponent, you think, okay, the human probably in the next lap he will take revenge, or they will take revenge on you and hit you back. So there's often this anthropomorphization that happens in this case. I think there was
Given that Gran Turismo has like real world, almost close to real world physics, this training of this AI and Sophy and everything, can that be extrapolated to a real world, let's say an AI self-driving racing car on the same track? It can.
I think that's a question that I get every time. I should include it in the slides. The main issue here is, as is very common in RL, our agents are very overfitted to this track and to the exact same dynamics. So I think as our colleague asked before, when you change something in the dynamics slightly, the agent doesn't work anymore. So I think because the simulation is pretty realistic, if you can do something like domain randomization, if you could do, I don't know, if you go vision-based and do some kind of image augmentation on that, I would believe it's possible to get a car to slowly drive around the track. One track that people always bring up is the Nürburgring, because I think the team is very proud how accurately they model it. So I've heard from the team sometimes they fly out to visit the track, to take pictures of the exact trees that are standing there, to model them exactly, and so on. So yeah, I think it would be possible. It's just that our whole training approach and goal would have to be reshaped in a significant way.
I think we can leave that question for now if you want, while we're having the lunch, the eating. But I think we could call it a day, especially for the people online. So thank you all for coming. Remember, next all on the 7th of June. And thank you very much, Florian, for coming.